Hello everyone. So in this lecture we will be studying about our DP optimization onto the recursive algorithm studied previously. So what was our algorithm, recursive algorithm, that we branch out with the help of the cases that whether the characters present at these two indices are equal or not. So if they were equal, then what we were doing, we were branching out, and if they were not, then we used to recurse for a particular scenario. So we had our base cases in here, we had our recurrence relation. So we will see that how to optimize this recursive tree with the help of tabulation approach in this case. So these are our base cases, and in the case when both of the characters present in the index are same, so we will be branching out, or else we will be recursing for this thing. So how do we fill now our DP table with the help of these recurrence relations and these base cases? So coming on to the first base case, so what we are having an empty string and we are having an empty pattern. So what did we do in this case? Now if we see in our recursive tree, we had this subproblem actually. We have an empty pattern, we have an empty string. So what did we return? The answer to this solution was 1. And what did that 1 signify? This 1 signified that from starting to this leaf, from this row to this leaf, I have found a pattern, or I have found a distinct subsequence. Hence the answer to this problem was 1. The same thing I will be doing over here. I will be entering a 1 over here. Each and every cell again in this matrix is actually a subproblem, which corresponds to a subproblem within our recursive tree. I think you keep in mind that thing. So what about this subproblem? This subproblem states that I have an R in my string, but I am not left even a single character in my pattern. So what is the answer to this subproblem? It would be again 1. The answer to RA in my string and not even a single character in my pattern, it would be again 1. And why am I filling this 1 again and again? What does this mean? Look, if I have nothing in my pattern, so what would I be filling in? What would be the answer to my subproblem? It is actually a base case. If I have nothing left in my pattern, then what I was returning? I was returning 1 over here. So each and every matrix cell is actually a subproblem. So here it corresponds to this thing, that if you are left something in string, so I have RA in string, but I have nothing left in my pattern. So what would I be returning over here? I would be returning a 1, and hence I have kept a 1 over here. The same way I would be entering a 1 over here as well, 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 and a 1 over here as well. So my first row would be complete with 1s. And what does this 1 signify? This 1 signifies all the base cases in which I actually returned 1 in my recursive tree, such as this base case I am talking about, where I have an empty pattern. I think if you would have branched out for most of these subproblems, then you would have encountered some cases in which you would have been left something in the string, but there was no pattern left. So in that case, how did you achieve that not even a single character in a pattern? Only when you would have received all of the characters within a string. The same way here, the same way this first row corresponds, and hence I filled up 1 over here. Now coming on to the code, how do I actually code it? I mean to say that all of my first row is actually would be having an answer of 1. So I would be traversing for all the columns in my 0th row, and the answer to these columns would be 1. Now coming on to our first column, what does this first column say? The intersection of an empty string but something in pattern. So there is something left in my pattern, but I do not left anything in my string. This column means that thing, that I am nothing left in my string, but I have left something in my pattern. So suppose in this case, what am I left with? I am nothing left in my string, but I am left with a pattern R to be made still. So can you make a pattern R with an empty string or in an empty string? No, you cannot make it. So what would I be filling in here? This is my base case, and this base case would be returning 0, and hence I would be filling 0 over here. The same way I would be filling 0 again. Why 0? What does this 0 signify? This 0 signifies that I am left with a pattern still, RA, but I do not have any characters left in my string to traverse in. So can I find an RA within an empty string? No, I cannot find it. Hence the answer to this thing would also be 0. The answer to this subproblem would also be 0. The answer to this subproblem would also be 0. The answer to this subproblem would also be 0, and the answer to this subproblem would also be 0. So my first column except 0 0 would be 0 over here. And I hope you would have understood why am I entering 0. Look, DP table is not about mugging up all the entries over here. Each and every entry makes sense, and each and every entry over here is actually a subproblem in the recursive tree. So don't mug up the values and how are we actually populating it. It needs to be done with the help of our base cases and with the help of our reconciliation. So how do we fill our first column in this case within the code? We can have a look over here. So what would I be doing? I would be populating my first column with zeros. And why am I doing that? Because I am nothing left in the string, but I do have some characters left in my pattern. So I would be traversing for each and every row, but mind you, starting from 1. I wouldn't be doing it with 0 because the answer to 0 0 is 1. I need to start from first row till end row in my 0th column. So that's what I have done over here. Let's see that whether our contents in my DP matrix are correct or not. Yes, they are correct. So we do have all the ones in my first row. We do have all zeros in our first column except this 0 0. Now how do we populate this thing? We can have a look over here now. So now we are done with our base cases. So we need to see that how to populate our other recursive problems over here. So what does this recursive problem mean, or what does this matrix cell means? This matrix cell means that I have a recursive problem where I have a character R in my string and I have a character R in my pattern. So I am talking about this thing, R comma R. So what was the first thing that we were doing? In each and every case we were checking that whether both the indices, the characters present at both the indices are same or not. So are they same in this case? Yes, they are. So what was I recursing for? I was recursing for that just tell me what are the total number of subsequences of my remaining string of my remaining pattern in my remaining string. So I would be recursing for this thing. And what was the other thing I was recursing for? That just tell me, okay, I found this character, it's fine, but can you find the same pattern again in the remaining string or not? So I was recursing for this thing. So where can I find this subproblem? This is this subproblem. So what would be the answer to this thing? The answer to this is 1. And where can I find this subproblem? It means then empty string and an R in my pattern. So an empty string and R in the pattern. So the answer to this subproblem is 0. So can you see how are we actually not recursing? Instead of recursing, we are just making use of the base cases to now derive solutions to our recursive subproblems. So this is the beauty of our DP matrix, that each and every subproblem in our recursive algorithm is actually a matrix cell in over here. So what will be the answer to R comma R? It's 1. Now what does this subproblem mean? This subproblem means that I have RA in my string and I have a character R present in my pattern. So what do? I will be looking that is this A, is this R same? No, they are not. So what was I doing in that case? I was saying, okay, they are not same, it's fine. Just tell me that what are the total number of distinct subsequences of my pattern in the remaining string. That's what I did over here. If you remember that now suppose this B and this I is not same. So what I was doing? I just recursed for my whole pattern in the remaining string because I cannot find this RABBI in the string which ends in a B. Hence I striked off this B and just told that just tell me what is the total number of distinct subsequences of this pattern present in my remaining string. That's what I would be doing over here. What are the total number of distinct subsequences present of this pattern R in my remaining string? So what is my remaining string? That's R. So where can I find this subproblem? R comma R. R in my string and R in my pattern. I can find it over here. So the answer to this would be 1. The same way, what would be the answer to this thing? It would be again 1. And why 1? Because what would I be recursing for? I would be recursing for, okay, B and R are not same. So just tell me what are the total number of distinct subsequences of this subproblem, and where can I find this subproblem? RA in my string and R in my pattern. It's this subproblem. So the answer to this subproblem would be this thing, and hence a 1 over here again. So the same way we would be populating our complete DP matrix. The last cell of this DP matrix would be our intended subproblem. What does it mean? That I need to find rabbbit or this pattern in my this string. So what will I recurse for? Is this t and this t same? Yes, it's same. So what would I be recursing for? I would be recursing for this rabbi and rabbi. And in the second branch, what would I be recursing for? I would be recursing for rabbi and rabbit. If you want to see in the recursive tree, that's why I recurse for rabbi in rabbi and whole of my pattern in my remaining string. So where can I find this subproblem? rabbi in my string and rabbi in my pattern. So that's the intersection of this I and this I is this subproblem. And where can I find this subproblem? This subproblem I can find over here where I have rabbi in my string and all of my characters in my pattern. So the intersection of this t and this I is actually this subproblem. So with the help of all these subproblems, we will devise a solution to our last matrix cell. So what does this subproblem mean? This subproblem actually means that what are the total number of distinct subsequences of my remaining pattern in my remaining string. This problem specifies that. And what does this subproblem mean? This subproblem means, okay, just tell me, what are the total number of distinct subsequences of my total pattern in my remaining string. Hence, this is the reconciliation over here. So now we will see that how to populate our DP matrix with the help of these reconciliation. So what do we see? That if my characters are same, so I need to branch out, and if they are not, then I will be making use of this reconciliation. So if we see the contents of our DP matrix now, what does this 3 mean? This 3 is actually the answer to our intended problem. And what does this signify? This signifies that the pattern rabbbit can be found thrice in my string rabbbit.